The remains of a planet that formed the moon may be hiding near Earth's core. In fact, a paper coming out today shows that high-density material in the mantle may be the remains of a Mars-sized planet. Now, these are some bold statements in my opinion, but modeling has shown how material ejected from the Earth by a massive collision could have formed the moon. Now the models are being used to look at what happened inside the Earth. Now, for those that don't know, seismic waves created by earthquakes, as they travel through the planet's interior, change speed and direction as they move through different materials. Things like rock type, density, and temperature all alter the travel of these waves, allowing scientists to gradually build up a picture of the Earth's crust and mantle. Spotting things like the rise of plumes of hot mantle material, as well as colder remains of tectonic plates that dropped off the surface of the Earth long ago and now rest near the outer core. There are some things that show up in these images, however, that aren't easy to explain. Deep in the Earth's mantle, there are two regions, and you're looking at them now. Two regions where seismic waves slow down, termed large, low-velocity provinces. This slowdown is consistent with the material being of higher density. So it's not really a surprise that they're sitting near the core. But that doesn't explain why there are two distinct regions, which you're looking at here, very distinct, both on opposite sides of the globe, slightly equatorial, but more southern. So it doesn't explain why there are two distinct regions of them or why they appear to contain material that has been there since the formation of the solar system. That's mind-blowing. But there is good news. Now, a team of scientists has tied these two regions' existence back to the catastrophic event that happened early in our solar system's history. A giant collision with a Mars-sized planet that ultimately created our moon in a moon boom. I know it's hard to explain, but a number of explanations for these large, low-velocity provinces have been offered, but none of them are entirely satisfactory. One idea is that they are leftovers from the process by which Earth's interior separated its crust mantle core structure. But the material should have been thoroughly churned up when a Mars-sized object, which has picked up the name Theia, smashed into early Earth, leaving enough debris in orbit to form the moon. Now, other suggestions include the idea that these might be the remains of tectonic plates that have sunk to unusual depths in the mantle. But this does not account for what this material looks like when mantle plumes bring some of it to the surface via volcanism. When sampled, the ratios of isotopes in gases trapped in this material look like those that were expected to be present in the early years of the solar system, or perhaps an asteroid, and not like those found in the current crust today. Now, the team behind the new paper, and kudos to them, suggests that a completely different source could explain the odd properties of these low-velocity provinces. Relative to Earth, the moon has a lot more iron oxide, which suggests that Theia also had a lot of this material. Now, since iron oxide is more dense than a lot of other mantle material, and by the way, Mars is red, a bunch of oxidized iron, but I do digress. It could explain that properties of the large, low-velocity provinces. In addition, the collision would have taken place early in the solar system history, which could explain why the isotope ratios look primordial. Now, the big problem with this idea is that it makes you dizzy when you look at it. Well, actually, that the material from Theia would have also been churned up in the wake of the collision. So it's hard to understand how it could form these discrete layers inside the Earth that have been stable for a very long time. So the researchers modeled the Earth's interior both during and after the collision to better understand how things might work, which is That's good news. We need the models. Now, there have been many models of the giant collisions between Earth and Theia. It's how we know it could have pushed enough material into the orbit to form the moon. But the team here took advantage of advances in computer power to perform these simulations at higher resolution than those done previously. Now that we have AI and we're about to be taken over by computers, you can understand why they went on this avenue. But in computing power to perform these simulations at higher resolution than those done previously that focused on the interior of the Earth, they also used two different modeling methods to ensure any results weren't specific to one approach or another. Now, these models showed that the post-collision melting of Earth would extend over halfway through the mantle, but there would be a fraction of the deep mantle that remains solid. And I believe we do have some graphs of that. And I may be missing it. Yeah, here. These are phase diagrams of the bulk silicate in Earth. The model showed that the post-collision melting of Earth would extend over halfway through the mantle. But there would be a fraction of the deep mantle that remains solid. Now, above the melt line, any material from Theia would end up thoroughly mixed with bits of Earth. But fragments of Theia would also end up injected below the melt line and therefore remain largely intact near the outer core, like we see here in these low velocity zone graphics. These would be, in fact, and have to be large pieces, and they would be scattered through the Earth's interior, but they would maintain Theia-like properties despite residing at a different planet. So the idea is that these large pieces fell into this capture zone and they can only melt in regions above the topography here, which we do see. Collectively, about 1% of Earth's mass would then be derived from these deep fragments. Obviously, this doesn't look like the two large low-velocity provinces we see today, which you're looking at here. But the Earth's interior has had over 4 billion years to evolve since the capture of our moon. To see what would happen with the Theia fragments over time, the researchers turned to yet another model of the viscous solid found in Earth's mantle. And by testing different conditions, the researchers showed that these fragments would sink close to the core as long as their density was at least 2.5% higher than Earth's. In addition, the chunks needed to be above a size threshold. Chunks that were just 25 kilometers across didn't sink, but 50 kilometers or larger did. The other clear outcome of this model is that the material sinks quickly. That's important because convection within the mantle would ultimately keep these chunks from pulling up. But convection would start in the upper mantle and gradually work its way down towards the outer core. The quick sinking allows the pieces of Theia to stay below where convection is happening, creating large pools of this material at the core mantle boundary in advance of convection reaching those depths. Now, what stands out from the models is that most of the results would seem to apply if there were regions of high-density material in the pre-collision Earth. Chunks of those could have been injected into deep mantle during the collision, and they would be difficult to distinguish from chunks of Theia. In any case, the idea is so provocative, or provocative enough, that it is likely to send a number of other planetary scientists back to the drawing board, which is what we need to do for all of cosmology. So kudos to the authors, and kudos to actual science, new science, breaking boundaries. Moon-forming impactor as a source of Earth's basal mantle anomalies will be linked below. And that's a boom to knowledge. Hope you got something out of the video. If you didn't understand some of the concepts I was talking about, please ask questions below and I'll be happy to answer them. Subscribe to the channel if you haven't. Share this channel with like-minded people as we are shadow banned because we talk about many controversial topics. And we love you. Be safe. And that's a boom.